All right, folks, let's get started. We will be finishing chapter 3 today. Really, it's just doing a lot of practice problems at the end of chapter 3 where we're talking about stoichiometry. But before we start, let's just look at some of the announcements I have written up here. So I do have my Zoom session tonight. I will still be holding office hours after class, so that gives me a little bit of a break to eat dinner, and then I'll have that Zoom session. So, there's a couple of ways to get to the Zoom session. It's in the announcement. There's a page that links to the webinar. You can find the page where modules, everything's on modules, all right? And so there's a link to the webinar. You have to be signed in via your OSU Zoom account. If you click on the link and it doesn't let you join, it's because you're not logged into your OSU Zoom account. And so there's instructions there on how to do it. So here are the commonly asked questions. Will I post the key? It's already posted. Will I record it? Yes, I will post the video link once Zoom gives it to me. I will post it on that same page where you clicked on the webinar link. Where? Yeah, same page as like the link. This probably won't be until like 10 p.m. honestly, because our session's over at 8:30. I have to drive home. Zoom takes time to like compile the video, so it probably won't be posted until 10, but I'll update you. Whenever I update a page, does it notify you that I updated it? Sometimes, maybe, okay, all right. Like when I post the recitation keys, I always hit like notify students that the page changed, so you know that like the recitation key was posted. All right, whatever. Other questions concerning the midterm. Lots of questions like, will we be given this, or that on the midterm? The resources page I have posted shows you exactly what you will be given on the midterm. So please look at that so you can reference that in your studies. Or, do I have to memorize X, Y, or Z? Again, if you look at that resources page and look at the exact supplemental packet that you will be given, you will know if you have to memorize it or not. Pretty much, yes, you have to memorize it. The only equation you are given is the kinetic energy equation. That's basically it. So please look at that file that I have posted there. Other questions I get. Is the exam multiple choice? It's a Carmen quiz. So yes, for the most part, it is multiple choice. Like we're not going to be having you input an entire, balanced chemical equation because we can't get Carmen to grade that. But there are some numerical input questions where you have to put in a number. And then last thing about the weather, I don't know. I don't know anything. I can't make any decisions about the exam tomorrow concerning the weather, but from what I know, we will follow what OSU does. So I don't know, just be on the lookout for announcements. Just assume that we are going to have it. I believe a decision has to be made pretty early because the first exam tomorrow is at like 9 a.m. All right, so I think a decision has to be made pretty early. All right, okay, and then the last thing, Daniel Turner posted a practice respondus test. It's just like a 3-question thing for you to test your respondus setup on the device you plan on taking your midterm. All right, so I have that linked in my page, and I think the department also has it linked on their practice midterms pages. So make sure you set up respondus on the device you plan on taking the midterm on, and then trying to access that, that quiz using the directions there to test your respondus. So I don't think there's any real chemistry questions in there. I didn't actually look at it, but it's just a dummy shell of a quiz so you can test it out. All right, any questions? How many people are going to come tonight? A lot of you? Okay, all right, awesome. And then the question is, where do you get this, the review packet I've posted? It's on that page with the webinar. So even if you don't come, you still have access to those practice questions and the key that's already up there. All right, so let's go to chapter 3. We left off talking about limiting reactants. And I asked you guys to think about this age-old question about making sandwiches. If I have 18 slices of cheese and 30 slices of bread, how many sandwiches can I make using this chemical reaction? 1 cheese plus 2 bread equals 1 sandwich. I feel like most of you can just do this in your head and you automatically get how many sandwiches can we make? 15? 15. And so I wanted you to think about this and discuss this with someone near you. What were the logical steps you took to get that number 15? Because I feel like most of us can get that pretty quickly, but really break it down. How did you come up with that number 15? And so talk about that with someone near you, about how you got that number 15. And you can't say, I just looked at it and knew it was 15, because that's not true. Yeah. What's up?
Do you know when we're supposed to find out where we take things down?
It's already posted.
On Carmen?
Carmen, yeah, it was like an announcement. I'm pretty sure it's Hitchcock something. Okay. All right, does anyone want to share? How did they get it? Does anyone want to share? Does anyone want to share? No one? No one? Okay, then I will tell you how I do it. But I'm a chemist, so maybe your way is a little bit different than my way. So I recognize here are my starting materials, my ingredients. I basically look at each of the starting ingredients and the reaction that I have and think, okay, I have 18 slices of cheese. If all of that cheese were to become sandwiches, I would make 18 sandwiches, right? Then I do the same type of process and think, okay, if I used up all of the bread and made the maximum number of sandwiches from the bread, I would see that with 30 slices of bread, I can only make 15 sandwiches because of the coefficients there, that I actually need 2 slices of bread for every sandwich. Is that kind of how we went about it? We took each ingredient kind of separately and thought, okay, what's the maximum amount? And you just pick the smallest number. That's exactly what you do when thinking about limiting reactants and stoichiometry in chemistry. So basically, those questions, how many sandwiches can you make given these materials? That's basically me saying, what is your theoretical yield? If you make the maximum amount of product, necessary or possible, that's your theoretical yield, in other words. Also, I can ask, what ingredient runs out first? We recognize that once we make our 15th sandwich, we run out of bread, and all we have is cheese left. So that's also something we call the limiting reactant. So in this case, the bread is the limiting reactant. And so we take this exact same strategy with chemistry. It's just not, cheese slices and bread slices. Now we're thinking about grams or moles of actual starting materials. But the strategy is to calculate, okay, if the maximum amount of each reactant goes to product, you compare those two masses, those two products at the end, and you pick the smaller one. It's the exact same thing. All right, and so there's the strategy there. And then I will talk about what's called a BCA table, and it allows us to kind of get a bigger picture of what is happening there. Okay, those are all my notes. So let's keep going with this analogy. All right, so we said we have 18 slices of cheese, 30 slices of bread. We identified that we make 15 sandwiches, and that bread was the limiting reactant. Let's think about this on the particulate level and think about, okay, if we took a snapshot of my kitchen table before this reaction, I would have 18 slices of cheese, right? There would be 18 slices of cheese, and then there would be 30 slices of bread, right? That's what my kitchen table would look like. But then after the reaction, after I make all the sandwiches, I make, the maximum, the theoretical yield, I make 15 sandwiches. But what this picture doesn't show, this after picture, is what I have left over. Can we think about what, if you did this and you made the maximum number of sandwiches on your kitchen table, what would be left over? Cheese. But how many slices of cheese? 3 slices of cheese, because you would recognize, okay, I have to use 15 of those slices to make the bread. So this picture is actually missing those 3 leftover pieces of cheese. And so this idea that we have to think about, okay, the reaction is consuming some of the reactants, all right? And then afterwards, there might be, we've made product, but we also have some reactant left over. So this is where a BCA table is really useful to help us understand the whole picture of what's going on. So BCA stands for before, change, and after. So before is we are trying to describe what's going on or what's in the container before the reaction occurs. So that's this sentence where I say you start with 18 slices of cheese and 30 slices of bread before the reaction starts. How many sandwiches do we have before the reaction starts? 0, all right, 0. All right, so that's before. I'm just describing my ingredients before. So this change line, this is what's dictated by stoichiometry, all right? So we identified our limiting reactant. Which one is that? Bread. So if it's the limiting reactant, it completely gets consumed, right? That I use up 30 slices of bread. So if I started with 30 slices and I consumed 30 slices, how many slices are there on my kitchen table afterwards? 0, right? So it's just 30 minus 30 equals 0. So this value, this negative, I consumed 30, this number helps us determine the other values in that change line. So if we inspect this, if we consume 30 pieces of bread, how many slices of cheese will we also have to consume? 15, because it's a 2-to-1 ratio. So it's minus 15. It's minus because we're consuming it. So another way to think about it in terms of the stoichiometry, I can say 30 bread, and then the coefficients here, 2-to-1. 2 breads is 1 cheese, and so see how bread cancels, and then we're left with 15 slices of cheese. So that's this step right here, stoichiometry. Okay? So that takes of the change line for the reactants, but we also need to think about, okay, how do the products change? So we think about if we consume 30 slices of bread, how many sandwiches do we make? We already said we make 15, so we add 15 here. And this works with stoichiometry as well. It's another 2-to-1 ratio. So if we start with 30 breads and use that relationship, 2 breads is 1 sandwich, CB2 equals 15 sandwiches there. All right, and then we just add things up. So 18 minus 15 is 3. And then 0 plus 15 is 15. So look at this after line and look at the box that we drew. So that after line, a BCA table really helps you see exactly what's happening within the whole reaction. So we know exactly how many moles of reactants and products that were made and consumed in the reaction, so we get a big picture of what is going on. So a BCA table before, change, and after can really help you take inventory of what's being consumed and what's being produced. But, you know, this was sandwiches, but we can also apply this to the concept of actual compounds, but all of the values in the BCA table need to be in the unit of moles. So keep that in mind. And then the change line is what's dictated by stoichiometry within there. Okay, so let's actually do some real stoichiometry examples with limiting reactants. So it's no different than the potassium example that we looked at, where we started with grams of potassium, went to moles of potassium, moles of your product, grams of your product. It's the same exact thing. But in this example, you're given 2 substances, amounts of 2 substances, right? You have aluminum and a mass of oxygen, so 2 different reactants. And it wants to know, how much of the product do you make? So the strategy here is do the calculation twice, right? Just like we did cheese and bread. You calculate what's the maximum sandwiches you can make with cheese, what's the maximum with bread, and then you pick the lower number, and that's it. So all we really need to do is just do stoichiometry twice. So these are skills you should already know from previous parts of this chapter. So I just go one at a time. Here I kind of saved us a little bit of time, and I wrote the molar masses of everything. This is a great way to start any type of question that you're approaching, getting the molar masses of the pertinent species here, because we'll need them. And note here, when I get the molar masses, so see how the coefficient 4 is here, 4 aluminums, but when I write the molar mass, I just am talking about the molar mass of 1 aluminum, 1 mole of aluminum. I don't take into account the 4 in a molar mass, because the 4 will be used and accounted for when we do stoichiometry, all right? Okay, so I will start with aluminum first. So I'll start with 60 grams of aluminum. All right, and so I want to get that to moles. So it's always gram, moles, moles, grams. So then 26.98 grams of aluminum is 1 mole of aluminum. Okay, and so what substance should I try to convert to? We're in the unit of grams, or we're in the unit of aluminum. What substance should I be trying to go to? Yeah, Al2O3, so that's aluminum oxide. Yes, because it's asking for the theoretical yields of aluminum oxide. So let's just calculate that so we can answer the question. And so we see the coefficients there is 4 to 2. So 4 moles of aluminum gives me 2 moles of aluminum oxide. And so now I'm in the unit of moles of aluminum oxide. I'll just go to grams. So then I can compare those two values in grams. So 1 mole Al2O3, 101.96 grams equals whatever. Then I'll set up my other one. I'll just do the calculation once because I'm lazy. So the other calculation, you just start with the other reactant and go to the product the same exact way. So we're just doing the calculation twice. So 96.0 grams of O2. The molar mass of O2, so 32.00 grams, 1 mole of O2. And so the relationship here is that 3 moles of O2 equals 2 moles of aluminum oxide. So I'm going to put 3 moles of O2, 2 moles the product, and then finally the molar mass to get the grams. 101.96 grams. All right, so there we go. So you actually have to do this calculation. Me personally, I can't just look at that and be like, oh yeah, that like aluminum is the limiting reactant. I can't do that. Also, I think a misconception students have is they'll just look at the masses and they'll be like, oh, 60 grams is less. That's less mass than O2. We can't do that either because remember, these reactions, chemical reactions, are dictated by mole ratios, that moles of substances are combining to make product, not grams. So if you do these calculations, you get that if all of the aluminum reacts, we get 113 grams of the aluminum oxide. I don't want to circle it. And then the other one, we get 203.9, or so 204 grams of aluminum oxide. Oh, I don't want to circle it. So from there, with those answers in mind, which reactant is the limiting reactant? Aluminum, because it made the smaller amount. So that means 113, this is the theoretical yield, and that means aluminum is the, the limiting reactant. Limiting. All right, and that would make O2 in excess. All right, okay, so someone might ask, okay, then what's the significance of 204? It actually means nothing. It means nothing. Because we could never make that much, because we would run out of aluminum first. Okay, so really limiting reactant questions are just 2 questions kind of in one. You just have to do two different analyses there. All right. So let's look at a different example. So that was doing, grams to moles to moles to grams. You will get super used to that. I hope you can do it 50 times before the midterm, something like that. We can also think about it on a particulate level, just like we did with our sandwiches. So here's a reaction. So I give you the balance reaction. We have nitrogen combining with 2 hydrogens, and we get 2 NH3s. Let's complete the picture. So it's just like sandwiches. So in my mind, I think, okay, in order to do the reaction, I need to eat a N2, so I'll just cross it out. And then I need to eat 3 H2s. So if I do that, if I eat an N2 and 3 H2s, what do I get in return? 2 NH3s, right? So I'm like looking at these coefficients. If I consume an N2 and a 3 H2s, I get 2 NH3s in return. So in my after line, I will get 2 NH3s. But then we can think to ourselves, can we do the reaction again? Yes. So if I eat an N2 and I eat 3 hydrogens, what will I get in return? 2 NH3s. So there's a total of 4 NH3s in the after picture. Am I done? No, because what's left over in that after picture that I haven't accounted for? That last little H2 there. So that actually goes over there also. Oops, so that will be in our picture too. But let's just think about, okay, so we completed the picture. That's what is there. We have a total of 4 NH3s, 1 H2 at the end. And so the question, which reactant is in excess? It would be H2, N2 would be the limiting reactant here. Let's just for fun do a BCA table to just like prove to ourselves that this is what's happening. So let me just delete my drawing here. So here's my BCA table. I just copied the thing. How many nitrogen molecules are there in the picture before the reaction? 2. How many H2 molecules are there? 2, 3, 4, 5, 6, 7. And then how many NH3s are there in the before picture? 0. All right. So if we kind of look at this, I mean, we already determined that N2 was the limiting reactant, but you can kind of see that here as well. Because if we minus 2, like subtract 2 N2s, we see that if we consume 2 N2s, we need to also consume 6 H2s, and we gain 4 NH3s. So then the after line is 0, 1, and 4. And that's actually exactly the picture that we drew, right? But let's just for a second pretend we didn't pick the right limiting reagent. Let's just, let me just delete this. Let's pretend, so it's what, 2, 7, 0? Let's pretend like you decided, no, H2 was the limiting reactant. All of the H2 reacts. So if all of the H2 reacts, so 7 H's, if we do stoichiometry, we see that we need 3 H2s, gives us, you need 1 N2, so that equals what, 7/3, which is equal to what? 7/3 is 2.33. So that means if I consume 7 hydrogens, I need to also consume 2.33 nitrogens. When you do 2 minus 2.33, you get negative 0.33. You get a negative number. So is that possible to have a negative after like molecule there? No. So that kind of proves in a different way that nitrogen is the limiting reactant. It can't be the other one. So that kind of is a way for you to check yourself that you chose the right thing, because if you keep going down the line and completing the picture with a BCA table, it won't make sense. All right. Okay, so there we go. How do we feel about that? I think this one's closer to sandwiches. Okay, all right. So here is the last part of chapter 3. So it's like really putting it all together, and that's the idea of percent yield. When we are in lab, even me, we are not perfect chemists. So when we do these calculations, you know, where we took aluminum, we went to moles of aluminum oxide, grams of aluminum oxide, we made the assumption that every single particle, atom of aluminum became product. Like 100% yield, that we did it perfectly. That's not how it is in the real world. Even when we make sandwiches, you know, we made the assumption that you successfully made every single sandwich, right? That every single slice of bread went to a sandwich. But in real life, that doesn't always happen. You know, accidents happen. You might drop some stuff. You might spill it, right? So the idea of percent yield is that we don't get everything that we calculated when doing the theoretical yield. So it's kind of like a grade, essentially. So your percent yield is shown as a percent where you take the ratio between the actual yield, so what you actually collect in the lab, over your theoretical yield. So your bottom part here, this is calculated. So the example when we did aluminum oxide, that when we got that number, what is it, 113 grams of aluminum oxide, that was our theoretical yield. So that goes on the bottom there. So actual yield is the value that you actually measure in lab. So just very generally, if a question involving percent yield, you typically have to calculate theoretical yield as well in order to get your actual yield if you're given a percent yield. So just kind of generally how to use this. So if our theoretical yield for a product of some reaction is 3.20 grams, so this is our theoretical, it says, but we only succeed in isolating 2.94 grams. Cross out moles, sorry, I messed up my units there. We need both of these to be in grams. What is the percent yield? So essentially, this is the maximum, 3.2 is the maximum you can get. You only got 2.94, so we just divide those two numbers to make that a percent. So in this case, percent yield would be 2.94 grams over 3.20 grams times 100. I think this is like an A minus. It's a 91.9% yield. All right, so that is a little bit straightforward. You know, recognize that maybe I don't give you the theoretical yield, so you would have to calculate that yourself before moving on to the next step for the actual yield. There's other ways we can ask it too. I think I have one or two examples here. Okay, so this example with it's both limiting reactants. We need to identify the limiting reactant and its percent yield. So we have 44 grams of nitrogen reacting with 8 grams of hydrogen to produce NH3 again. If this reaction only produced 37 grams, what is the percent yield? So I recognize that 37 grams, that is my actual. And so it's asking for percent yield. So we got our actual, but we need to figure out what our theoretical is here. And so we can determine that from the ingredient, the grams, the masses of the ingredients that we're starting with to calculate, okay, if all of that reacts, all of the limiting reactant reacts, how much NH3 are we going to make? So this question is really no different than that aluminum oxide question. We just have to take it one step further with percent yield then. So it's the same exact thing. I always like to start with the molar masses because I have to use them eventually. So make sure you know how to do that because I'm skipping that step. So I just start with the mass of each of them and individually go to the product and then compare. So 44.0 grams of N2. We use the molar mass of N2, so that is 28.02 grams, 1 mole of N2. Now it's stoichiometry. What number goes on the bottom here? On the denominator? 1. And then what goes up top? 2 NH3. Yeah, so 2 moles of NH3 and then 1 mole of N2. And then I would just go to grams because you have to do that anyway to get percent yield. So 1 mole NH3, 17.03 grams. Boom. Okay, now we do the other one. 8 grams of H2. Use the molar mass, so 2.016 grams, 1 mole H2. Now for stoichiometry, what number goes on the bottom? 3, yep. So now that we're doing stoichiometry, remember, when you use the balanced chemical equation, you have to be in the unit of moles, and that's what we did. So 1 mole of NH3, and then molar mass of ammonia again. I'm just going to copy it because I'm lazy. There we go. All right, and so you stick that into your calculator, and you get, the first one is 53.48 grams of NH3. It should be 3 sig figs there. But this isn't our answer, keep in mind. And then we have 45.05 grams of NH3. So which reactant is our limiting? H2. All right, so our theoretical yield is our 45 number there. So it should have 3 sig figs. It's 45.1 grams of NH3. Is that our answer? No. Yes, question? Oh, it should be 2. This right here? Yeah? Okay. Nice catch, because these numbers always match the coefficients in the balanced chemical equation. I think these numbers are still right. All right, so 45.1 grams, that's not our answer. We need to make that into our percent. So we know how much we collected. It's 37 grams, so that's over 45.1 grams, and then times 100, it's a B minus. So 82 point, I didn't get the decimal place, percent. It should have 3 sig figs. Okay. All right, so that question really no different than the aluminum oxide question we did. We just had one tiny little step at the end to get that percent yield. So recognize that it's implied that you must calculate your theoretical yield first before you calculate your percent yield. Okay, so, I wanted to do my demonstration. Okay, let's do my demo now. So this is the last question in the chapter. It's another percent yield. We just do it a little bit differently. So I want to do a demo. It's the volcano thing where we take vinegar and baking soda. So this reaction, I am taking vinegar, so acetic acid, it's an acid, and I am combining it with sodium bicarbonate, CO3, okay? And one of the products is CO2, gas. So this isn't a balanced reaction, don't worry about it. But what I want you to see here are the ratios, the mole ratios. So when everything's balanced, it's a 1:1:1 ratio. All right, so within this demonstration that I want to do, I have 3 bottles over there. I wanted to bring this. I have 3 bottles over there. In one of the flasks, so in the first, so I have, flask 1, flask 2, and flask 3. In flask 1, I have the sodium bicarbonate is the limiting reactant. So I basically only have, I have 0.2 moles of my acetic acid in the container. But then I only have about 0.05 moles of your bicarbonate, the other thing. In the second container, I double the amount of sodium bicarbonate, so it's 0.1 moles, but I still have 0.2 moles of the acetic acid. And then finally, in the last one, I have regular stoichiometric amounts of both of the things. So if we think about this, how much, if we look at these coefficients, 1:1:1:1, and think about which container, CO2 is a gas, and it's going to flip up or fill up these balloons, right? All right, so why don't I do that? So in this container, I have is the first one, where I have the sodium bicarbonate is the limiting. So let's just do that. All right, and they told me I have to shake it up a little bit. So this says it has 4 grams, but it's the sodium bicarbonate is the limiting reactant. So I'm just going to do all of them at the same time. So this one has double the amount of sodium bicarbonate, so hopefully we see something different. Oh, geez. Is that allowed? I don't know. And in this last one, we have equal number of moles of sodium bicarbonate and acetic acid. Okay, so it's a little bit more. Oh, geez. Oh, I forgot my goggles. Oh, there we go. Okay, so hopefully we see that this balloon is the smallest. This one's a little bit bigger. And this one's the biggest. Wouldn't you say? It's kind of a little bit hard to see because volume doesn't translate into increased circumference as well for volume measurements. But what we see is that we have the smallest here because sodium bicarbonate is the limiting reactant, and over here we have equal amounts. But I want you to think about, what if we doubled the amount of sodium bicarbonate again, and we did this reaction again? If we doubled, so how many grams of sodium bicarbonate are in this one? 16 grams? What if we put 32 grams of sodium bicarbonate in a fourth container? Would we see the balloon go double in size? No, it wouldn't, because then what is the limiting reactant if we double the amount of sodium bicarbonate? It's the acetic acid, and the amount of product, the amount of CO2 would be the exact same. All right, and I should have had the fourth balloon, and then we'd predict it, but whatever. You get it, right? Okay, so that's my demo. Let's do the very last question here. Oh yeah, this one. Where's my pen? Oh no, it's over there. So when thinking about percent yields, we can, when we do that ratio, we can do it in moles or grams. It doesn't matter as long as the units match. So in this example, we're talking about the same reaction, but moles of components. So we have 2 moles of N2. It's reacting with 9 moles of H2 to produce NH3, so same thing. If the reaction has a 65% yield, how much NH3 in grams was produced? So same idea within here. So if we have the amounts of starting materials, so from there we can determine theoretical yield. Theoretical. So if we recall what percent yield is, it's actual over theoretical. So in this case, we are given the percent yield. We still need to calculate theoretical yield, and so we are just back calculating the actual yield here because we're given the percent. So it's really no different than the previous question that we just did, right? Except, instead of calculating the percent yield, given the actual yield that we collected, it's kind of working backwards here. So same idea. We start with, hydrogen and figure out how much NH3 we make. We start with nitrogen, figure out how much NH3 we make. We pick the smallest one there. So I will just start with nitrogen because it's written first. So it's nice here. It's written in moles, so I don't have to use molar mass of nitrogen. It's already in moles, so that's nice. I can go straight to using the balanced chemical equation. So 1 mole of N2 is 2 moles of NH3, and then molar mass of NH3. So 1 mole, 17.03 grams NH3, boom. Now I do 9 moles of H2. So the ratio is 3 to 2 NH3, and then molar mass of NH3. Did I do it right that time? All right, so stick that into your calculator. You get that the 2 moles of N2 makes 68 grams of NH3, and the 9 moles of H2 makes 102 grams of NH3. So here the pertinent value is 68. This would be our theoretical. 102 actually means nothing. It means nothing. It means nothing to us. But what this means is that 68 grams of NH3, because it originated from N2. N2 is our, limiting reactant here, while H2 would be in excess. All right, is 68 our answer? No, it's not. So we take 68 times, the 0.65% yield. We got, what's 65%? Is that a C or is that a D? Oh, that's a D. It's a D, yeah. So then we got a lot less than that. And so whatever that is, I think it's 44 grams. Okay, so, or you can, we're plugging in 68 into the denominator here. Yield is 0.65, and then you're solving for your actual what's on the numerator within there. All right. There's actually, I want to do one more thing here. I want to do one more question expanding on this one. So we determined that N2 was the limiting, and that means H2 is in excess. Let's calculate how many grams of H2 is left. Do you want to do that? Yeah, let's do that. So When trying to determine what's left, oftentimes doing a BCA table is useful. Let's do a BCA table. I don't have the answers to this. So let's set up a BCA table. Why don't we? So I'm just going to copy this. Copy, paste. Okay, we can see that. So what are we starting with? 9 and 2. So 2 moles of nitrogen, 9 moles of H2. So B, C, A. So from here, so recall that in BCA tables, we always need to be in the unit of moles. All right. So from here, we also know that there's 0 moles of NH3. We determined which one was the limiting reactant. N2 was the limiting reactant. You should see that also, because if we do minus 2 moles of N2, if we think about 2 moles of N2, and ask ourselves, okay, how many moles of H2 will have to be also consumed? We look at the stoichiometry. 1 mole of N2 consumes 3 moles of H2. So total, we need to consume 6 moles of H2. Right, so that's a minus 6 there. All right, for hydrogen. And then we can think, okay, now let's go to nitrogen to ammonia. So plus what value will go here in our change line? 4, because you can do the stoichiometry too, or you can think, okay, for every 1 mole of N2, we make 2 moles of NH3. So if I consume 2 moles, I'll get 4 moles out. And then it's just the math. So I'm just adding up each column. So 9 minus 6 is 3 moles. I consume all my N2, so that's 0, and then I have 4 moles of NH3. So at the end of the reaction, I will have 3 moles of hydrogen left. And then you can convert that to grams if you want to, right? Can we do another one with that question? Yeah, do you have a question? 102.
That's the theoretical with 9 moles of H2 minus the theoretical with...
So 102 means nothing to us. If you do the subtraction there, I'm trying to think of what that means. I don't know the significance. So it's in the unit of grams of NH3. So I'm not sure if there's any significance there. I would have to think about it. Okay, all right. Okay, let's do one more question. Using the same thing. Can I delete this? Can I delete it? Sorry, I'm going to delete it. All right. So you do this reaction again. You have you start with a container of N2 and H2. So there's no NH3. And at the end of the reaction, you have 6 moles of NH3 and 2 moles of H2, 0. And then 0 moles of N2. What did you start with? What did you start with? Let's think about it. So I'm giving you the second box of the picture. You need to back calculate and figure out, what did you start with? Just change all the words to cheese, bread, and sandwiches, and I think you can get it. If you just change the word NH3 to sandwich, right? If you make 6 sandwiches, and for every 1 cheese, you get 2 sandwiches, let's just say. If you make 6 sandwiches, how many pieces of cheese did you need to put into the reaction? Yeah, 3. Because of the stoichiometry, right? Because it's like Planck's Sudoku, right? What needs to go right here? 6, but specifically plus 6, because we gained NH3. Okay, so 6 NH3s. We ask ourselves, if I make 6 NH3s, so 6 moles of NH3, obviously, using stoichiometry, how many moles of N2 did I need to start with? So we do the stoichiometry: 2 NH3s, 1 N2. So that's 3 N2s that we needed. So I will put 3 here, but is it plus or minus? Minus, because it got consumed. And then I do the same thing with the other reactant. So 6 NH3. Okay, then I look at the coefficients here. So it's 2 to 3. So 2 moles of NH3 requires 3 moles of H2. So how much H2 was required for this reaction? 9 moles of H2. So I'm going to put a 9 here. Is it plus 9 or minus 9? Minus 9, because it got consumed. Now do you see where we're going here? Okay, so what did we have to start with in order for us to subtract 9 moles of H2 to get 2 moles of H2? 11. And then N2, 3. See that? Yeah. We didn't have to. We didn't have to know the limiting reactant. But if you just looked at the after line, you can determine which one is the limiting reactant. Because in all of our examples here, the limiting reactant gets completely used up. So in this case, N2 would be the limiting reactant. But we really didn't need to know that. Because what was important here was that we knew how much NH3 we made. And that from there, we can determine, okay, how much of the reactants did I need to have? So for example, if I make 12 sandwiches, see, I could change this to sandwiches and you'll get it. Why don't we do that? If I change this to sandwiches, you'll totally get it. So what is it? 1 cheese, 2 breads, 1 sandwich. Okay, B, C, A. You start with 0 sandwiches. After I'm done, slaving away in the kitchen, I have 8 slices of cheese, 5 slices of bread, and 13 sandwiches. What did I start with? What did I start with? So what's the first step here? What's the first thing we recognize? I made how many? I made 13 sandwiches, right? So in this change line, I made 13 sandwiches. So from there, can't we predict how many slices of cheese and how much bread we used from there? So how many slices of cheese did I need? 13. Oh, sorry, is it plus 13 or minus 13? Minus, I needed to consume that. And then how many slices of bread did I need to consume? 26. Boom. Same thing. Same thing. So really the idea here is that because we knew that we started with 0 here and we ended up with 13, I can fill in this change line and determine everything else. And so I don't know what the answer is. 21 and something, what is that, 31? Okay, I'm not very good at math. Yeah? Would it be perfect? No? I mean, if I have 21 slices of cheese and 31 slices of bread in my kitchen, do I have to make the maximum number of sandwiches from the ingredients there? Yeah, so in this example, we actually didn't go to completion. But that's okay, reactions can happen that way too. But the way we treated this reaction and the one previous, it's the exact same steps.
If there were leftovers for both, would they both be limiting reactions?
So in this case, since we can't really have like a fraction of a cheese, the analogy doesn't relate as well, because if it was N2 and H2, even if there were fractions, one of them would run out, probably, unless it was exact stoichiometric equivalence, that it was exactly like 2 moles to 1 mole of molecules there. Okay, so we have like 7 minutes left. Do we want to do practice problems in chapter 3, 2, or 1? Which one? 3, okay, so let's just scroll down a little bit and we'll do some questions at the end here. And I'll save those Zoom questions for later. Okay, so do we want to do empirical formula? Yes, okay. So let's just do this one. What is the empirical formula for a compound that is carbon, hydrogen, and oxygen? So with empirical formulas, my cheat to this, it's not even a cheat. Maybe if I call it like a hack, then you guys will remember it. With empirical formulas, you start with a gram amount of your elements. You convert all of that to a mole amount of those elements. From there, this is where you divide by the smallest one and you get the mole ratio. And then from there, you can get your empirical formula. All empirical formulas work this way. So we aren't given masses, we're given percentages. So the easiest way is just to assume that those are grams, or that you have a 100-gram sample. So I just convert those percentages into grams of each component. So 26.4 grams of carbon, 3.3 grams of hydrogen, and then 7.3 grams of oxygen. So I got grams. Now I need to convert to moles of each of those elements. So carbon, what's the molar mass of carbon? 12.01. Do you need to memorize that? No. But have you guys already memorized it? Yeah, I know. And hydrogen is 1.008 grams, 1 mole. And then oxygen is 16.00. 1 mole of oxygen. Hydrogen, there we go. All right? And so you do that, you get some numbers. So if you inspect units here, we're in the unit of moles, so 2.198 moles of carbon. This is 3.27 moles of hydrogen. And then this one is 4.39 moles of oxygen. So you might be saying, Dr. Nguyen, you're not really doing sig figs here. It doesn't really matter because we're just going to divide by the smallest number and get integer values anyway. So sig figs here don't really matter. So what's the next step? Is this my empirical formula? C 2.2, H 3.3, oxygen 4.4? No, I've never seen anything like that. So the strategy here is you just identify the smallest one and you divide everything by that number. All right, and so that ensures that carbon is a mole of 1. So carbon becomes 1, hydrogen becomes 1.48, and then oxygen becomes 2. Okay, so is that my formula? No. Can I round 1.48 hydrogens to 1? No. In my mind, I think, oh, that's really close to what number? 1.5 hydrogens. So then I recognize, okay, 0.5, I can get rid of that by just multiplying everything by 2. So that means that the empirical formula, so this would be the mole ratio. 1 carbon, 1.5 hydrogen, 2 oxygens. That's the mole ratio, but to make it an empirical formula where everything's whole numbers, I have to multiply all of them by 2. So C2, H 3, thank you, oxygen 4. That's the empirical. All right, so that's the simplest ratio of atoms. So what piece of information do I need to get the molecular formula? Molar mass. So if I just added okay, here's the molar mass of this compound, what's the molecular formula, and not the empirical, you go through the exact same steps, and then you compare the mass of this, what we just calculated, to the full mass of the molecule, and you just kind of scale up. So it's the exact same steps. You don't have to relearn something else. It's the exact same steps, yeah. Wait, if you're given the molecular formula, then we don't need to do an empirical formula calculation.
Wait, well, we can modify the atomic masses or the substance because we know it's that many atoms.
Yes. If you have a molecule, that's how you calculate molecular mass. So I have still 2 minutes, so I will keep going. So combustion analysis is a little bit different, but it's the exact same steps, right? So recall with empirical formulas, our goal, right, is to do this, to do grams of your elements to moles of your elements to your empirical formula. So in a combustion analysis, this part is the exact same. We need to get, so our compound only has carbon and hydrogen in it. So our goal is to get moles of carbon and moles of hydrogen. But instead of starting with grams of carbon and hydrogen, we're given gram amounts of CO2 and water instead. So it's just a little different way to go about it. So I'll start the first one for you. So it says we have CO2, so 5.86 milligrams of CO2. So I'll just convert that to grams really quick. So -3 grams of CO2. So here, do I use 12.01 or do I use 44.01? 44.01, because that is the molar mass of CO2. Because we're in grams of CO2, we need to use the molar mass of CO2. So grams, 1 mole of CO2, and then the step that I always do, even though it's a 1, I know, 1 mole of CO2 is 1 mole of carbon, because that is our goal here to do. It's the same type of empirical formula stuff, and then boom, that's it. But then we have to do it for hydrogen as well. So the other piece of information, 1.37 times 10 to the -3 grams of H2O. Same thing, use molar mass of H2O. So 18.02 grams, 1 mole of H2O. But then what do I put here in this last thing? Yeah, you need that too, where 1 mole of H2O is 2 moles of hydrogen. So there you go. You got your 2 numbers, and it's the same exact empirical formula stuff as before. So the only difference between this question and the previous question is how we got to moles of each of those elements. So they're basically the exact same thing. All right, and once you know how to do one, you know how to do them all. All right, I'll still have office hours. I'll see you at 6:30.